I will focus on vortex aspects, but of equal interest is magnetic fields or quantum aspects, which are covered partly here. So vortical flows in classical and superfluid turbulence, vortex knot spectrum in turbulence, and then adapted knot polynomials from helicity and a topological cascade as geodesics in a knot polynomial space and optimal geodesics for evolutionary path. The last point would be topological approach to superfluid turbulence, which is a very, very arrogant way to end up my lecture, but the hope in science is always driving force. Now, what about vortices in fluids? Oh gosh, we all know that these are there since ancient Greek time. I studied Anaxagora, Anaximene, and Anaximandro, the three ones who put forward the theory of vortices for the universe. And we are back to, I don't know when, ask Sophia for this, but Leonardo had, his computer simulation coming from here were so perfect. And you see here the swirling flow of water coming from, again, Euler equations, we may say, because this is very regular and this becomes almost chaotic, not entirely chaotic, as Leonardo tells us. So this is a lesson from his work. And then we had a poet's version of turbulence. Big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, so on to viscosity. Pay attention to these rhymes because I propose my own rhymes along Richardson. All right, so here is a group of people, you're young, the leader from Peking University now, showing us a simulation of vorticity visualization of the Navier-Stokes equation. A now retired professor in Peking, and Chang-Su She, at the time in Princeton, gave me this picture that was then published in Nature, where at the time, 1990, with Orszag, they were able to visualize a bundle of vortex filament, coding the intensity with the colors, as you see, an amazing work. And then we have back to modern time, the group of Hussein, this time with Yu Yang and the guy Jie Yao is in Beijing Institute of Technology, Yu Yang in Peking. DNS, direct numerical simulation of a topological cascade of a vortex made of a trefoil shape, done under Navier-Stokes equation. So you have reconnections everywhere, and then it keeps going. The bridges of vorticity left behind, as shown before, and then finally the two structure. You start with a structure of this size, you end up with those. This is what we saw many times, the evolution of a trefoil forming a half link, and then a convoluted one loop, and then further reconnections may be here in forming two separate, barely visible, separate unknotted loops. All right, so this is the cascade I am paying attention to, and we could follow the same thing in quantum vortex dynamics, production of a Hopf-link, etc. Two or one color, one unknotted convoluted loop, and finally two distinct, barely visible, but there's a dark blue and a pale light blue there. This is again the drawing of Feynman to emphasize the anti-parallel situation and then the breakup into smaller scale structures. Now, we worked on polynomials with my good friend Xin Yu. We met in Normale. He visited me in the year 2011 or 10, and there we went at the board and he said, so give me a big problem that is unsolved that I love to work with you. And then I said, you really want to go for the big one? Okay, let's talk about turbulence. And this is the idea. So I said, I tried or I strive to have not polynomials in the turbulence picture, but it's hard. I don't know how to do it. And we discussed at a certain point, taking the idea from Vasiliev, E to something, then we thought well, maybe E to helicity can be a good one. Remember, if helicity, you interpret helicity as a helicity for a single filament, we have the benefit that we can decouple this contribution in terms of rise and twist. And why not? Maybe we can identify the variables of the Hopf-Lee PT with the function of twist and function of rise. So we would give some physical, yes, geometric, but also physical sense to the polynomial. I have to warn you, whatever I do from now on is almost based on ideas. I don't know if it will work till now. So we have now a number of projects in several directions, certainly in Beijing. They are very, very keen to explore this, possibly other places. So we don't know if all this works. So it's just kind of pure mathematics so far as we go. What we did, well, we tested on something that we knew was working, maybe, and so we considered the following test case. Remember, we went in Irvine's experiment from the trefoil to the Hopf-Lee, unknotted and two separate loops, but we could start from anything here in the sequence of torus, knots, and links and see if it works. And so we made some assumptions. All knots and links in this sequence are elements of this family. Then we consider the topological complexity decreases by a single stepwise reconnection. Of course, multiple reconnections can take place in a physical system. You can think of, I remember Lou once told me, well, if you have three strands interacting on one point, the surgery or whatever, you can decompose this as a sequence of two strands interacting in sequence. So you can decouple the multiple nodal point to a multiplicity of simple nodal reconnection, nodal points reconnections. So you go, degree 3 can be decomposed in 2, degree 2, or 3, degree 2 in a graph diagram. Topological changes occurs by a single orientation preserving reconnection. I would say orientation preserving, I would add anti-parallel reconnection to make things simple. And this is the way. Remember, you go from, let's say, a knot to a link, to a knot, to a link. All the time you apply a reconnection. All right, so you can work out by using standard scheme relation, the recursive relation for torus knots and links that allows you to, starting from the initial trefoil and the Hopf-link polynomial, you can produce high order polynomials according to this relation. And then you set numbers, pure numbers, to these A and Z. Where these A and Z are, these A and Z are in the Hopf-Lee PT polynomial, and they are related to twist and right. So you can even compute exactly the twist and right of the embedding of a trefoil knot or a torus knot or a torus link. Precisely, you would get different numbers. You would get a different monotonic decreasing function of complexity, but basically it's the same exact diagram shifted up and down in a particular scale. So this is the diagram I refer to. And when you compute these quantities according to these numbers, you see that the Hopf-Lee PT value, numerical value, is now like this and going down, monotonically, decreasing. Keep in mind these sequence of decreasing values because it will come up in a moment in a different context. All right, so we were pleased about that. What about Jones? Well, you know very well how to reduce Hopf-Lee PT to Jones, and you reduce everything to the variable t, and this t can be a function of only twist or only right. For Jones, I showed you that in particular case for quantum vortices, helicity is exactly zero. Self-linking number, if there is one component, is exactly zero. That means the amount of twist is compensated by the amount of right. So this function t of can be t of right or t of twist. Doesn't matter. All right. So now we have the beautiful work. I don't know why the slide is like that. Probably I didn't want to show Luke Kaufman's contribution, but he's in there with William Irvin, etc. And they investigated the cascade of this type of knots and links. And the diagram provided in the paper is quite interesting. And again, you see a cascade of structures, different topological complexity. I pushed, or I encouraged a student of Xinliu to consider a similar strategy starting from the Borromean rings. So he set up in a computer the Borromean ring vortex link, and then he let it evolve according to Gross-Pitayevsky. So according to Gross-Pitayevsky, you may expect that by changing the geometry, the local geometry, then the evolutionary path may be different because the system evolves naturally according to the initial condition. Certainly what emerges is the production, the abundant production of whited links and then connected Hopf links, trefoil knots Hopf link, and then this degeneration towards loops. One of the first diagrams he considered was a possible decay path of in different directions, but they all go towards the connected disjoint connected sum of loops, unknotted, a number of them. It was a long work. This is the main author, is a postdoc now working in artificial intelligence, Hao Wan in Beijing, with the code provided by Simone Zucker. All right, we go back from classical to quantum. As I showed you this transparency before, you can identify a line of quantum vorticity as a line, as the skeleton of a vortex filament. So you can study this, you can use the same initial conditions, and you can verify numerically that this complex network of filaments are actually the skeleton of the real vortex filament in Navier-Stokes equation. And the other message you have to carry home is that you start with a complex network, you let it evolve, and as it evolves, it goes down in complexity, consistently with what I said. Yes, John.
Did you also check the time scale of different paths, like the speed, how fast they decompose with different geometrical conditions, different paths?
Of course, data are there. We paid attention not to the level you mean. You mean if we have precise measurements of the time evolution from, say, a snapshot, a topological state to the other.
Yes.
We didn't do that, but it can be done.
It could be interesting to know if different paths has like different
consider
speed,
that,
let's say.
Yeah, consider that in the diagram that you saw sketched by hand, there are at least 20 different paths considered.
Yeah, you told me about the
it's
you already
some
told
work.
me about everything. Yeah,
It's some work. Let's be open to, it is a lot of work, and you are not really sure what you get out of it.
Sure.
So that's why you hesitate to put so much work into that.
Sure.
That's the only reason.
Okay.
But in China, you can do things.
Here's another question before you leave those cascades. If we start with a torus knot of type PQ, we know that the reconnection number is P minus 1 times Q minus. So that means that we can compare the cascades and the Humphrey polynomial values that are going along with that fact that it's going to take at least that much. And it may be that the P minus 1 times Q minus 1 occurs in the Humphrey polynomials. If we look for it, it won't be obvious from the Humphrey polynomial why it has to do with reconnection, but it might be there nonetheless. So I'm curious about your Humphrey polynomial.
I follow you very well. I know
whether that kind of thing is sitting.
Absolutely, thank you. And surely is
and the same remark goes for the Humphrey polynomials. There's a big experiment because you can take any positive knot, and we know the reconnection number in terms of something, and then we can see whether those numbers are in the Humphrey polynomials, and maybe we end up with a conjecture about the Humphrey polynomials that way.
Agree word by word. Yeah,
Yeah.
thank you. Okay, so at the time when Diane, probably you were there too, I remember Lou, in Beijing, 2019, at a certain point we went to a place where the Carlo Berenghi was keen to explore what we were saying. Here is Rob Sherine, Xin Liu, and Eric Rodon. Hao Wan is here, and this is a young man that has collaborated with us later. His name is Yongrong Zhu. And okay, so this is an important picture for Carlo in particular, because then he published this paper, Not Spectrum of Turbulence. Amazing, very interesting work, because he applied a useful polynomial, the Alexander polynomial, probably also easier to compute, but not to quantify stuff as I propose you to do in terms of right and twist, etc., but just to measure the topological complexity of the vortices that were appearing in his evolution. So we are talking superfluid evolution, so helium-4 evolution, and what he found that complex structures are decreasing consistently with what we expect. The point is that he found the Alexander polynomial, if we take the degree of the polynomial as a crude measure of complexity, he got a degree of the order, if I'm not wrong, of the order of 30, 35. So I put him in touch with various experts, Eric in particular, Eric Rodon, etc. Nobody has the ability to compute such a complex knots. I like to tell you a story, a few seconds. When I was in Japan, at a certain point, Keith Moffat came to me and said, so Renzo, I know you are keen to explore vortex dynamics with knot theory. And I said, yes. And he said, but come on, more than the trefoil knot you want find. And he had in mind classical vortex dynamics. And I replied, why do you think like that? In superfluids, you can get a very intricate networks of filaments. That was maybe 15 years earlier than this work. And here is the proof that yes, very complex knot types and links, etc., form in superfluids and possibly will be detected in classical fluids. I expect the group of you younger can make progress soon in that direction. Okay, so you remember we can state a correspondence between the Humphrey PT polynomial and what I call the adapted polynomial. The adapted polynomial carries information also about the flux, the intensity of the strength of the vortex. So it becomes, in a sense, a time-dependent function of the physics other than geometry and topology. And same can be done for Jones. So because Jones is a bit simpler, I'll stick to Jones, and I invite you to follow me this presentation. So we want to find a way to measure, because we now are going to consider each polynomial value, each polynomial as giving us a numerical value for the topology and the physical information it carries. So I want to find the measure, the distance between one object and the other. In other words, I want to find the distance between one polynomial value and the other polynomial value. As I said, I repeat, each polynomial value identifies simultaneously the topology of the system and, let's say, geometric and physical information of that system. So the idea goes like this: a topological change is suddenly due to a single reconnection at a time, just for a start, and not a link is identified by the Jones polynomial. We go to adapted version of this Jones polynomial to come up with numerical values, so that for the unknot is 1, for a half link is this number, according to an average value of right and twist, let's say, the trefoil knot, this number, and so on and so forth. You see, we get numerical numbers. And we want to relate how this is distant from this, is distant from the other, etc. So the idea is back to Einstein, as Alicia said, you put a lot of mass and you think of the curved space-time that is a measure of the amount of mass. I come from the mountains, so I didn't like this one. I reversed the situation. I said the complex knot is on the peak of the mountain and it goes down to the sea. Everybody wants to go to the seaside, enjoy sun and sand, etc. So here is my mountain view of the same idea. I am on top there with maybe a torus knot 27, and by an optimal path, I don't want to die in the vertical direction. I want to slowly go down to some nice path. I go round, and at a certain point, all my energies go down. I start to feel tired. I become a trefoil knot, and then finally I go for a bath. And there I am, the unknot is the dream wish of my wife to get me thin. All right. It's a 30 years dream of my wife.
There's a new way to connect knots and mountaineering. Mountaineering or two.
Don't tell me. I know how to connect knots and mountaineering because it's a way to get saved from something or save myself from somebody. Yeah, of course. Now polynomial space. What is this thing? Well, it's just a visual representation here. Is an n-dimensional n, being the degree of the Jones polynomial is a discrete made by points, Euclidean space endowed by the metric, given by the complete polynomials of orthogonal types. So we have to transform or relate the Jones polynomial to some polynomial for which we can compute the metric. And so the inner product has to be there, and we took Legendre polynomial. Why Legendre? It's a long story. Legendre, Hermite, even Jacobi, they work all the same. You change polynomial of this type and you get maybe slightly different numbers, but basically the same algebraic structure. You want to make the basis orthonormal, so you divide it by this quantity, and then you use a standard result in algebra, a polynomial Vn, not the Jones polynomial, a polynomial Vn up to n degree can be expanded to first n plus 1 Legendre polynomials, which provide a complete basis for your space. So this is the space I aim at, and I want to identify the Jones polynomial with this Vn, and being n the degree of the Jones polynomial. So when I do this, I expand the polynomial in this form where there's a Ci are the coefficients associated with the Legendre structure, and they are basically the coordinates C0, C1, C2 of the point in my metric space. So this point has these three features. On one hand is the coefficients of the Legendre decomposition. On the other hand, it represents a knot type whose polynomial, third attribute, is the polynomial of that knot type. All right, so this is the approach, and we went to data. For data, we use the data provided by Mariel Vasquez's group, and of course, some mention Shimokawa working there on the band surgery techniques, and they consider the 2-6 knots. Actually, they consider even higher classes of knot, but let's say 2-6 knot, and we have different pathways that the given knot through the action of enzymes reconnect and change its topology. You know, the percentages put here are computed also on the basis of theorems and on the basis of direct computations that tells you the probability that this knot type goes in this direction. And so you see that the dominant feature is this cascade. And this cascade is through torus knots and links. And this is the same cascade that I showed you before by implementing Humphrey PT values. So we had a test case to run against, and okay, we did. This is the main feature they found. There is something you notice that at the end, for example, there is 97.3% that goes in this direction, 99%, so you don't have 100%. It means that there is some maybe reconnection taking place and generating higher complex structures, etc. In our case, it's simpler in a sense, because we have now a way to define the distance the distance, the reference distance normalized, everything is the straight distance from the most complex knot we have and the unknot. And then identifying the decaying path, we identifying 2 different paths that they didn't consider. So we have 17 paths. For each path, we have to compute all the information. So here there are other 3 and then other 4. So altogether we have 17 paths, and right, and then we consider the most simple approach of, let's say, probability is just elementary algebra. We define a relative deviation from the straight cascade, and then we compute the probability, and the unlinking probability patterns are given here. You see that when we are at this stage, we have 100% of probability to go down here, because there is nothing in between in our sense. If we compare numbers, this is first of all the optimal pathway, and if you compare the numbers with them, we are doing pretty well, because the red numbers are our numbers, and you see how close they are. Of course, sometimes there are differences. In this case, 3.8 and 0.2, 3.7 and 0.4. But roughly speaking, we are doing pretty well. So we are pretty confident that this approach might work for the future. And now we go for the future, because you are tired, I'm tired too. Please go on.
Can you go back
Sure.
last slide? I remember for the Borromeans, you have differences in left and right structure. Here, can you tell something about, like, if there is some sort of probability to fall in the left of the trefoil, the right of the trefoil, which is the difference? Because I feel like it's more the geometrical, like, assessment of
2020,
Yes,
6 years
yes,
ago.
yes.
Now we have more results. Let me
Okay.
go to more results, and then we may discuss it, because this has been on and on and on, and a lot of work came after that. Okay, so sorry, I go next slide. We define some kind of measure of this topological complexity. There are many definitions of topological complexity. We took one that we felt appropriate. This is what you saw so far. This is another way to present the same thing, but because the diagram is much bigger, it tells you immediately something, right? Okay, so this is the cascade. I included the cascade considered by Lou and William Irvine, etc. So it's hidden there. This is the straight cascade for torus knots and links, and all the others are there. So the new results now. So we are going to show you the new stuff. We use adapted Alexander Conway polynomial, no difference, same results. So I'm not going to show you this. We use the Hermite polynomial basis instead of Legendre. No difference, basically, a little difference between values, but the trend is the same. So we are fine with that. And we computed the topological complexity, whatever you may call it, all knots and links composite up to 6 crossing. That was done by Lou's work and others. So that includes a Borromean 6 crossings. Okay, and now we moved to consider all possible knots with 6 crossings, i.e. composite included, and we had 20 more, and then we keep going, and we had the 7 crossing knots examined. There are 34. So you say, okay, you examine 100 more knots. No. 800 more knots, because you reverse orientability, you end up with the same knot type. I can't remember the technical word for that. You consider mirror images, maybe they have the same polynomial. So many more, and we have now a table of all these listed in an Excel file. It's a huge file, 800, more or less, 800 knot types were considered. And composites, right? And we went on. What is not visible, I'm sorry, but if you see the real picture, there is an area here, well distinct from the other. Imagine that this is a pink area, and this is pale blue, that's why it's not visible. The pale blue area goes across here, and the pink area goes here. They are separate, and they stay separate with 1 or 2 possible misplaced situation where all the knots with either positive or negative powers stay in one region and all the other knots with mixed positive and negative powers in the other region. So you can measure what is technically known as the spread of the polynomial, and you measure the spread that is very close to equality. There is an inequality detected by Licorice and others, and so the spread in the polynomial expression is consistent with what is expected in theory. So all this was done, and we added 8 crossings. Now,
What did you mean that they stay in that region in terms of the dynamics of the reconnection? What are you saying?
Not yet dynamics. These are numerical values from the polynomials. And there is, wait, one more slide.
Saying the polynomials behave in a certain way for this region and for that region.
That's right. That's right. Okay, we went up to 8 crossings. All the 8 crossings we could detect, detect in the theory of knot theory, composites, links, knots, everything, mirror images, whatever you like. And again, you don't see it, but there is an area here that separates the all positive, negative from the mixed exponents, with these ones highlighted in the pink that should belong to the pink region, but they somehow are in the light region. So there are some very few. The number of knots, let's say, misplaced in this context is below 7%. So every 100 knots, you may have 1, 2, 3, maximum 6, 7 that are not in the bright colored region. Now, why this? First, the trends are well separated and stay well separated. This trend is not a decaying path, is not representing a decaying path, it's just representing the numerical values of the polynomial. If we go back to the actual decaying path, you should go what was known from your work and known work. So we don't know what's going on here between, say, this knot type and this knot type. Is this knot type cascading to here or not? We don't know, because there are no two-day experiment done with 8 crossing knots decay. The maximum we have is 6 crossing from the Borromean rings down. I want to go back my slides, and this is what is given here. So here, these connected segments, these are the cascades that have been checked happening. For example, here nothing happened for these knot types. Somewhere maybe this A represent, I can't remember, the Borromean ring, because this includes 6 crossings. And so these are all the cascade tested so far. And the important point is that these are well separated. One is here in red, one is here in orange, one is here in blue, and one is this one in various colors. These separation, this is the green dot, is the trifoil, this is off link, this is the unknot. Then this is one family, this is the other family. So evidently we have the 4 crossing family, 5 crossing family, 6 crossing family. And then we go on 7 crossing family. And then finally we get to the 8 crossing family. So far, this is the work has been submitted, and the future work is to go to 2 variable polynomial. We have to find one polynomial of the Legendre type that is able to work with 2 variables, to extend this to Humphrey PT, relate topological cascade, of course, to information entropy, because it's very close. The definition of Shannon entropy is so close to our information, because after all, is topology talking. So if we convert topology to numerical values, exactly is a la Shannon. And then relate topological entropy a la Shannon to energy, or physical entropy to energy decay, and establish possibly in the long term, so to speak, I'm not so young anymore, topological theory of turbulence cascade. So my Richardson rhymes can be converted from big whales, have little whales that feed on their nose. wheels, lesser wheels, so on to viscosity, comes big knots have little knots that feed on their topology, and little knots have just a knot that disappear into vacuity. That's all. Thank you very much.